Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our review for applied linear algebra and numerical analysis. So in the previous video, we've talked about spans and linear independence, and I'm pretty sure we also talked about linear combinations as a starting point before explaining span and linear independence, right? And in the previous video, we talked about vectors pretty much. So in today's video, we're going to be going over a homework. And I believe this is homework 0. Let me just, okay. You know what, maybe before I start the video, I have to have the homework prepared, or else I'm gonna take screenshots of it. It's fine. Anyway, okay, so where was it? Hey, math. Okay, give me a sec. I'm gonna pull up the homework real quick. Homework 0. Okay. This would be okay, cool. Let's do the homework. Okay, let me just where are you? So just pull up the PDF file. I don't want to pull up the text file anymore. Too much hassle. Right. Let me go through number 1. So number 1's pretty basic, I would say. At least for me, I think this one's personally easy. We can just go through it quickly. Okay. This is more of a homework 0 review. I'm gonna put homework 0. So consider the following vectors. So we have V and W. So surprisingly, they put it in physics notation. And we're being asked to compute the following ABC, right? So what are the topics here that we've discussed so far? So topics here, again, I would list them down. We talked about the idea of vector addition, and this was in the first lecture. We also talked about scalar multiplication. And we even talked about how we can combine these two to get vector subtraction, but I'm not gonna include that anymore because these are the building blocks we need. And of course, vectors, right? I'm kidding, I'm not gonna. But yeah, just to briefly recap what those are. So just a quick solve was 2v. This is the same thing as 2 times the vector itself. And we would just multiply the scalar to each component. So we would get -4, 6, 2. And we're done. B is the same idea, right? We're multiplying it by a scalar -1. And so we have components -1, 1, 4. So we would get 1, -1, -4. Nice and easy. Last one. So here we combine both ideas. So we're doing scalar multiplication as well as vector addition. But we're combining these ideas. So we do 2 of the first vector. So that's, or actually, we just write the first vector. We already have it. So this is from part A, -4, 6, 2, minus 3 of W. So that is -1, 1, 4. If I keep going, this would be, I'm just going to add it. So this becomes +3, -3, -12. And I think I would get -1, 3, -10. Okay, let me check if my answers are correct, because of course, we have to check, right? Okay, A is correct, B is correct, I think, and C is correct. Okay, nice. Yeah, so that's the idea of number one, right? We're just applying scalar multiplication and vector addition. Cool. Okay, let me do number two. So, oh, this is funny. I'm gonna zoom out a bit. There we go. So here we're being asked to determine if the following sets of vectors are linearly independent or linearly dependent, and we give a justification. So how do we do that, right? Based on what we've discussed, it's linearly independent if we only have the trivial solution where our scalars, in this case our alpha scalars, are all zero. But if one of them is non-zero and we say it's a solution, it works, then they're dependent, right? And the other definition, which I'm going to be honest, I did forget what that definition was. The other definition was if we have a collection of vectors, they're linearly independent if none of the VJs can be written as a non-trivial linear combination of the rest. So I think we did a proving here. Here we know this is dependent because we can write, I think we did the example here. We can write V2 as a linear combination of V1 with a scalar of 3. This is a non-trivial linear combination. So we could do that. But I would say the easiest way is to just do the alternate definition because it's a more systematic way. But we could do the first definition, right? So just to briefly recap, right? So recap, if we can write VJ as a non-trivial combination. I'm not gonna write linear anymore. I'm gonna assume it's linear because we're doing linear algebra. So we're only we're only doing linear objects as a non-trivial linear combination of other. Actually, let me do VK to make it different. I don't wanna assume they're the same thing, you know? I can't see. There you go. Let me do VK here. Other VJs. Okay, here's where I do the VJs. If we can do that, then we say they are dependent, right? Or did I mix it up? I probably mixed it up. Oh, I can't see. Oh, they're dependent. If we can write it, right? Yeah, I'm right. Then the set of VK and the VJs, this is not a way to write it, is dependent. This is a dependent set, right? Otherwise, independent set. That was the first definition, right? And there was a second definition. That's the first definition. The second definition was that given alpha 1, v1, all the way to n, alpha n, vn, equals 0, if alpha 1 is equal to alpha n equal to 0, the set of v1 to vn is independent. Otherwise, dependent. So we only have that trivial solution where all the scalars are zero, then we know they're independent. The set of the vectors are independent. Otherwise, it's dependent if there's a non-trivial solution of the scalars. So these two, we did a proof of why these two are the same. Okay. Right. Let me see. What am I gonna say? Oh yeah, let's now answer the things. Okay. Let's do A. So A here is actually, I would say A is easy, right? 3 pi. What do you notice about A? If we let, okay, let's do this. If we let V1 be the first vector and V2 be that second vector, it's funny enough because this was very similar to an example I did. What can we say about it? Are they dependent or independent? Since V2 is actually just 3 times V1, this set of V1 and V2 is dependent. Because we can write V2 as a linear combination of V1. Since V2 is a non-trivial linear combination of V1, right? This is true. Now, what else can I say? I could do the alternate definition where I put a scalar next to them, and I could see if I get a solution out of it. But if I only get the zero, then that means they are independent. But in this case, they're dependent. This thing's dependent. Right? Okay, let me try B. Oh, goodness me. So B here has a very big number. We have 1 pi, and we have, I think this was 3 and 9 point something. Oh, goodness me. Okay. 9.424777. I'm lazy, so I'm going to do a variable. Okay. 960769379. Okay, that humongous number, I'm gonna copy and paste it. I'm gonna say, oh, uh-oh, my thing's not working. We let S be equal to this. I'll just do S. Okay? That's not 5, that's an S. How do I think that? That's an S, that's not 5. Cool. Okay, so we have this, and what we're trying to do is determine if this set of vectors are linearly dependent or independent. So how do we do that? Well, for one, we could try writing the other as a linear combination of the other. So we could do like what we did here. If we could find something, I think we could do that. That one's a really good way to do it. Okay. Another thing we could try is do the alternate definition. But in this case, I would just try doing this because we only have 2 vectors anyway. So we need to find, I guess, scalar k such that this thing is equal to k of this thing. Yes. Is there a thing? So that would be, we have 1 equals, this is actually just a linear system at the end of the day, which is 1 equals 3k, phi equals sk, right? Here we see we got 3, but then here we don't get 3, right? So here apparently no solution. This system is inconsistent, has no solution. Hence, the set of V1, V2 is, since it has no solution, it's independent. If there was a solution, it would be dependent. Last time I did this, I'm pretty sure I keep doing the alternative version. But here I'm going to try doing this, the first definition. Because, I mean, we only have two vectors in there, so, right? It should work. Okay, here in letter C, we have 3 vectors. So I think this is where we need to do that. Okay, so I'm gonna do this. 2, 2, 0. I think this was 1, 0, 1. This was 0, negative 1, negative 1. And, well, based off of this, do we know the set is dependent or independent? Well, there's one way to find out, right? Let's try the alternate definition. But if we could write one of them as a linear combination of the two, we immediately know it's dependent. If we can't do that, we know it's, what do you call this? We know it's independent. Okay? So I'm going to do, so I'm going to let V1 be that first vector, V2 be that second vector, V3 be third vector. And then from there, okay, I'm going to try, we let alpha 1, alpha 2, alpha 3. These are scalars. So we say, is there alpha 1, u1, alpha 2, v2, alpha 3, v3 equals 0 such that alpha 1, alpha 2, alpha 3 equals 0. If there is, or actually, if there is another solution, then set is dependent. Okay, so let's try. How I would do this though, I would just do some linear algebra, Gaussian elimination, see what works. You know what I mean? But that's the idea. So let me just do it. We have 2, 2, 0, 1, 0, 1, 0, negative 1, negative 1. I would convert it to an augmented matrix. This is something that wasn't taught in this course, but we are allowed to use it as long as we know how to do it. Here I would do this. I actually just subtract. So we get 0. Oh crap. 1 minus 1 and 0 zeros. Okay. Okay, this looks right to me. Let me see. 2 minus. So what I did here was row 1 minus row 2. I put in row 2. So that's 2 minus 2 is 0. 1 minus 0 is 1. 0 minus negative 1 is 1. 0 minus 0 is 0. And then based off of here, I think I can do another one. So we do row 2 minus row 3. So we get to what we call echelon form. So this one's going to be, this one's staying the same. This one, though, is staying the same. This one's different. 0. This is 2, 0. And from there, we can do back substitution. So we say alpha 3, or in this case, oh, look at that. What do we notice? It has a pivot in every column, this augmented matrix. So since matrix has pivot every column, set is, so we know if it has a pivot every column, then set is independent. Because alpha can only be, all the alphas here are 0. There can't be another solution. We can try using back substitution, but based off of experience, here we see alpha 3 is 0. Alpha 2 and alpha 3 are 0. Alpha 1 and alpha 2 are 0. Okay? So this is independent. So this matrix in echelon form has a pivot every column. So the set is independent. Cool. Okay, let me try last one. Okay, that was taught in my other algebra class, linear algebra class, but it's pretty much the same thing. We could do it in a more systematic way. Here, can we shortcut this? I don't know. 1, 1, 0. Can we write it? 1, 1, 1 plus 0. Ah, I don't think so. Let's see. Actually, I'm not sure. Based off just looking at this, can we see one vector that we can write as a linear combination of the rest? If there is, the set is dependent. I'm trying to look, but I can't seem to find any. So worst case scenario, we use that alternate definition where we just do it by brute force. So I think we can do that. Okay, let's do it. So again, we have a set of vectors, and this is 1, 1, 0. We have 1, 0, 1. We have 0, 1, 1. We have 4, negative 4, 4. And I believe these are, okay, I can't really eyeball it. So we're just gonna check how I would do this. 1, 1, 0, 1, 0, 1, 0, 1, 1, 4, negative 4, 4. So actually, funny thing is there won't be a pivot every call. Actually, let's check. I don't wanna, I'm not too sure. So let me see. Oh wait, no, there is no pivot every column. Is there a pivot every column? We can only have 1, 2, 3 pivots. We can't have a fourth pivot. So actually, here's the thing. We don't even have to, we can just eyeball it. So there is no pivot in the fourth column. Even if we convert it to row echelon form, there isn't going to be a pivot in the fourth column. This is guaranteed. Or if there is, there's going to be some free variable somewhere. So at the top of my head, this is, well, it's dependent. So it's either there's no pivot in one of the columns, or one of the columns, or there is slash r free variable somewhere. So the set is dependent. Just eyeballing it. Of course, if this were a test, I would write out. I would do the alternate definition because that's what I'm used to. I'm just trying to do new ways of proving this idea. So if we check the answers, let me see. So these are, the first one's dependent. First one's dependent, yeah. Second one is, what is this? What? Independent. Yeah. Third one is, I said independent. Third one is independent. Yeah. Oh, I should have. Okay. And then fourth one is dependent. Yeah. Correct. Cool. Okay. Let's try the last. No, not the last one. Here we're being asked to solve the systems. No, the linear system. So let me just do that. So here I could do the most boring way, not the most boring way. I could just do it through elimination, substitution, things that we know from high school. But that's kind of boring, so I'm gonna do something fun. I'm gonna do it in a linear algebra style. I'm gonna do 3, 2, -1, 1, 2, -2, 4, -2. Feel free to try this one. I think this one's easier for me. Also because I've been doing this for what, 6 weeks? So I think this might be easier. So what I could do here, I could divide by half row 2, plop it back to row 2. So this would be 1. This would be 1, -1 in this case. This would be a 2. And then this would be -1. And I think now I could do this. Row 2 minus row 3, or add it actually. We put the row 3. Here we get, oh, I could do that. 0, -1/2, 2 minus 1 is 1, -1. Okay, we just added these together, basically. Did I get this right? Hopefully I did. -1 plus 1/2, it's -1/2. What else? What else? What else? What else? 1 minus 1, 0. 2 minus 1 is 1. Okay, I think I got it. And then from here, I'd probably multiply this. Actually, I don't want to do that. Yeah, I would multiply 3 by 2 because I want to get rid of the fraction. So this one's going to be a -1. Downside this is 2. Both of these are 2. Okay. And then from there, I think I can do another one. Now we make this 0. So 3 I divide by 1/3. Row 1, subtract that to row 2, put that in row 2. So that would look like, this would be 1 over 3, to 1 over 3, 1 over 3. I would keep row 3 the same. Row 2 is going to be different now. So 1 minus 1 is 0. 2/3 minus -1, that's 5/3. And then -1/3 minus 2. So this is, I believe, minus 7/3. And then I think 1/3 plus 3/3, 4/3. And then how I would do this is I would multiply row 1 by a 3, put that in row 1, and then also multiply row 2 by 3, put that in row 2. So the way that's going to look like is there's going to be a 3. There's a 2, -1, 1. And this one's going to be 5, -7. This one's a 4. So when I'm scaling it, it's pretty much the same thing. And then, well, I would divide this by a 5. This one I would leave alone. And then I would divide you by a 5. Row 2, add it to row 3, put in row 3. Here I would do 0, 0. This one would be 1, -7/5, 4/5. And this one is 1 minus 1, 0, -7/5 plus 2, 10/5, that's 3/5. Then we have 4/5 minus 2, so minus 2, that's -6/5. And then again, I would multiply row 1, no, not row 1, row 2 by 5, and then row 3 by 5 as well. So this would bring me back to this original one, 5, -7, 4. I just don't want to work with fractions. And this one would give me 3, -6, which is a nice number. Oh, okay, I could simplify this. I could say 5, because I multiplied by 5. Now I divide it by 3. So I could do 5 divided by 3, 5/3. So this one will then give me 1, -2. And there we have it, clean matrix. Cool. Okay, so now that we have that, we have a pivot every column, so we know this is independent. And what else can we say? Oh, we have to solve it. Okay. So x sub 3 is -2. So here we're just back substituting. 5x sub 2 minus 7x sub 3. Well, that's the same thing as 5x sub 2 minus 7 -2. And this would be 4. So based off of that, we get 5x sub 2 plus 14 equals 4. 4 minus 14, -10. Here we would get 10. And then we divide by 5. X sub 2 is -2. And then lastly, on top, we get 3 to -1, 3x sub 1, 2x sub 2 minus x sub 3 equals 1. So this is 3x sub 1 plus 2 times -2 minus -2 is equal to 1. So this would give me 3x sub 1 minus 4 plus 2. Minus 4 plus 2 is -2 equals 1. This is 3. Then x sub 1 is 1. Can't erase. Uh-oh. OneNote's not responding. Funny. Okay, back to 1 And there we have it. Those are our solutions for that linear system. Cool. Okay, that's number three. And I think the last one, yeah, last one's pretty self-explanatory. So this one is something that I, I did a little bit before in when I was reviewing. So again, we go back to this idea of Pythagorean theorem. And well, what do we know? We want to find the length of the following vectors. So we want to find the magnitude. So that's going to be the norm of this guy. How do we do that? Well, we just do square root 1 squared plus 1 squared, square root 2, or that's it, square root of 2. Then we want to find the length again, so we do the norm, the Euclidean norm. So that is square root of a squared plus b squared. That's it. Okay, let me just check if they're correct. I feel like I might have gotten it wrong at some point. We'll see. Okay, it's nice how they kind of organize this. Oh, there we go. Cool. Yeah, they organized it. It was really nice. Square root 2. Nice. Okay, so that's it for this video. Pretty short, pretty simple. I hope you guys enjoyed, and I'll see you all in the next video.